Stanford University.
But I will talk about cars. I'm a professor here, colleague of Larry's, in computer science and electrical engineering. In fact, you're being housed in the electrical engineering facility today. And I work on the future of the automobile. So I know that you're all design people. I really appreciate your existence in this universe because you make my life so much easier. My knowledge about design is weak. I would never get a paper accepted at this conference. So the only way for me to give a talk is with a keynote. Makes it easy for me. No rejection, no submission. But what I wish to do with my 35, 40 minutes is to make you aware of technologies that are in the make right now at Stanford and elsewhere that will really influence the sector of transportation. If you go and look at society at large, and I pulled up a random technology, computing, and ask ourselves what happened in the last, say, 60, 70 years. I went back to Google and checked out what a computer looked like in 1940. At the time, computer was still a job title. Moved into the 1980s, and in 2009. What you find is, thank you, that these devices look so dissimilar from the previous generation that if you were to fall asleep in 1940 and ask a person who wakes up in 1980, can you operate a computer, they had no clue what to do with it. In the space where I operate, it's very different. If you go to cars and transportation, 1940, here's a Cadillac, 1980, a BMW, 2009, a Tesla, an electric vehicle. Basically, nothing really happened. In the sense that if you were to wake up a person who fell asleep in 1940 today and show him a Tesla, he might be amazed by the fact that there's no gas involved. But there's still a steering wheel, there's still brakes, they work exactly the same way, turn signals, 4 tires, the things that goes forwards, not sideways, it doesn't fly, as we all had been made believe by the Jacksons a long time ago. It's the same thing. Innovation in the space of transportation, and specifically the automobile, has been unbelievably slow. It's not for lack of announcement. Here's a recent announcement I found by GM in 2005, just before the Grand Challenge, an event I'll tell you about. They announced for 2008 the first self-driving car, but these announcements have been with us for a long, long time. Now, how bad is it really? We can argue that the digital revolution changed the world. We now have very different modes of communication. Television, broadcast media, print media is all being affected by small little innovations like digital storage of information. In the transportation world, these changes are not there, and it's not for lack of opportunity. I put together a few statistics which I hope you can read, which I'm going to briefly go through, about the horrendous inefficiency of traffic and transportation today. Apart from the about 1.2 million people that die every year in the world due to traffic accidents. Traffic accidents are now the #1 cause of death for young people. I think #2 is suicide, turns out. There's a recent study actually that shows that texting, let's see, who here has ever texted while driving? Oh, come on. I don't believe your words. Okay. I think pretty much everybody has, okay. Texting makes driving even 3 times more risky, so there's new technologies that make driving even more dangerous than it was in the past. Commuting. We spend an average of 46 minutes a day in the United States on our way to and from work alone, in a car, doing nothing particularly productive other than making phone calls and listening to the radio. There's entire groups of people excluded from the driving experience that could be included, like blind people, disabled people, elderly people, kids. Energy is interesting because energy is being discussed a lot these days. We all think about transportation, the next big innovation wave will come from electric cars and so on. That's actually a good thing to discuss. It turns out, depending on how you calculate, between 28 and 30% of the nation's energy is being used by cars, mostly badly, inefficiently. For example, in trucking, if you make trucks that drive very close together at 10-meter range, you can save up to 21% of the gas consumption of the trailing trucks. So if you just had technology to link them together closer, you could save significant energy. We lose billions of gallons every year in just traffic jams, just waiting for the traffic to clear up. And we're using cars itself very efficiently. Let me ask a second question. Who here owns a car? Okay, that's pretty much everybody, right? So what's your car doing right now? Okay. It's standing somewhere, right? You probably have a rental car too, that's also parked somewhere. You're unbelievably irresponsible, right? So you're just tied up 2 vehicles, 55 vehicles, and you're using them something like 4% of the lifetime. So a lot of resources go into just manufacture of those cars, storage of those cars, your garages and so on, the heat surrounding your car, and disposal of cars. The last number I'm going to give you is highway congestion, which is an increasing problem here in the United States, also probably your home country. There's a growth rate of about 3% of highway use in this country every year, without any new highway construction of any significance. If you look at highway operations, you'll find it's grossly inefficient, okay? The way you can do this is, say you land on San Francisco Airport, you take a look from the air at a highway, say 101, and the highway, say, is really busy, it has the highest possible throughput. A highway can give about a vehicle every 2 seconds, about 2,000 vehicles per lane per hour. And say you take a picture of that highway and ask yourself, how much of the real estate highway is actually taken by cars versus how much real estate is still available? When you look at the picture from the air and count how much pixels are pavement, how much pixels are cars, you'll find that only about 8% of the real estate is actually physically occupied by cars, whereas 92% is still empty. And what that means is that a busy highway is basically empty. If you could invent technology that let us drive slightly closer together and maybe keep our lanes better so we can make them smaller, so we could go from, say, 8% occupancy to 16% occupancy, we're still 84% empty. You just double the nation's capacity highway system. You just double the capacity of the nation's highway system. The small innovations that I think are long overdue could really change the nature of traffic. And that's what my talk is all about. So I will tell you about something work that we did at Stanford a couple of years ago until the present day on making cars smarter. And the way I'm going to start is with a little story that starts with the US government, DARPA in particular, the Department of Defense branch for advanced research projects. DARPA had been investing in unmanned vehicles for a long time. They invested, I think, in the order of about $500 million on research, mostly to major defense contractors and major universities like Carnegie Mellon. And that led nowhere. So DARPA in 2004 came up with a new idea. It said, look, if you can't get our work done by funding institutions, let's get our work done by not funding institutions. Instead, let them offer $1 million as a prize money. If you can build a car that can drive itself all the way from from Los Angeles to Las Vegas, without a person inside, completely autonomous, no human driver whatsoever. Okay. Now, it turns out it was a crazy idea. DARPA issued this map just before the challenge. It didn't go from Los Angeles to Vegas. It went from Barstow, California to Primm. Reason being there's just too many kids playing in Vegas or in Los Angeles, which is too dangerous. And they found a nice desert trail that looked a bit like these pictures over here, and specified the course through a set of GPS breadcrumbs, about 2,000 of those, and asked those cars to drive out, follow these breadcrumbs, and within 10 hours, master the 140-mile long course, 142 miles. So here's a movie that DARPA made of that specific event, the first grand challenge. About 100 teams signed up for it. About 15 were permitted as finalists. This is the frontrunner Carnegie Mellon, which had the strongest team at the time, a remodified Humvee, completely driverless. There's no person inside. There's just a computer governing all the decisions. This is a smaller vehicle. Some of them were homegrown, where some universities or companies built entire chassis from scratch. Others were more like regular cars, like this vehicle from Caltech, that is, of course, modified to be able to perceive the environment and make decisions. This is a local team. They actually are specialized in production of subwoofers, and they found this $1 million price thing a great way to make more money. This is a major defense contractor that never debugged their control system. It actually flipped over right after the camera stops. The largest vehicle, 30,000 pounds. This is a military vehicle used by the Marines heavily. They had a little software glitch, so they went further backwards than forwards. Never mind. And the smallest contestant, is anybody here from Cal? If you're from Cal, feel free to leave the presentation at some point. This is Cal. It's not a little. Actually, a person I actually admire, Anthony Lewandowski. He worked so hard on this that he forgot to switch on the stability of the motorcycle. So I walked up to him after the competition and asked him, hey, what's your goal for next year? And he said, I'm going to double my performance. So did DARPA. DARPA, realizing that the furthest vehicle had gone was about 7 miles out of 140, said maybe we should just do the same thing with twice as much money. At the time, $1 million was a lot of money. Today it isn't anymore. Today we talk about trillions. But at the time it looked like a lot of money, and they just doubled it from year 1 to year 2. So we got involved. Just to show you the effect on the people, the teams involved. This is the teams in 2004, 106 of those, and this is what doubling the prize money does. If you look at this map very carefully, it's highly correlated with states scoring Democratic in elections. I wonder why. So Stanford is somewhere over here. It's misspelled with a D, like Stanford, as opposed to a Sidford. Anyhow, so I decided to enter the race at the time because I figured it's a great challenge and I can make $2 million. But I had no money, no funding. So instead of what you normally do is you recruit graduate students and you pay them, or you recruit your staff at a company. I decided to start a course called CS'09 Projects in AI, and instead of giving my students money, I would give them course credits. So together with Volkswagen, we actually very rapidly built up a vehicle. Just this is a regular SUV, it's called a Touareg, it's a really nice off-road vehicle. And what we did is we put a trunk full of computing equipment in there, and we had these wonderful buttons over here. This one is actually the one that guaranteed I'm still alive today. Every time there was a software bug, I would hit this button and rescue myself and switch from robotic control to manual control. We plastered the vehicle with sensors that are able to understand the environment and make driving decisions, which I'll talk about a little bit later. There's 2 groups of sensors here. One is related to your own positioning, GPS-based sensors. They're usually used for vehicle guidance. And one set of sensors, cameras and lasers, that can assess the terrain around the robot and make driving decisions to avoid collisions with obstacles. It's always good to go back to the early days. This is probably a couple of weeks into the class. This is doing initial tests where we try to avoid little paper boxes on top of the medical parking garage. And you can see on the left the vehicle doing this. On the right, you can see an internal map built by the vehicle. The interesting thing here is this medical parking garage used to be full of cars. And our students would just work there day and night. And every time someone picked up his car, he asked what's going on, and we would tell them what's going on. So sooner or later, no one parked there anymore. Later in the game, now I'm going forward about 8 months. This is just before the competition started. Here you can see our robot Stanley descending through a desert trail. There's people inside as a safety backup. It goes about 40, 50 miles per hour, which is relatively fast in the desert, turns out. But it's completely autonomous, which means the car drives itself. It's given this set of breadcrumbs as before, so it knows where to go, but it has to make all the driving decisions, the microscopic driving decision like speed and steering by itself. Here's a sandbank. This is a fairly steep descent. You can see a little bush. Unfortunately, the robot is unable to discriminate between this bush and rocks. So it avoids these bushes, so it's really environmentally friendly. It's just not very pleasant for the people inside the car to have to swim around these obstacles. And it regulates its speed at the same time. Sometimes getting really slow because the ground might be very rugged, like as shown over here. Some of the technologies that lead to these kind of behaviors, I'll just give you a very brief rundown. This is a laser-based system. What it does is it uses a scanning laser, a laser light beam, that is emitted from the vehicle platform. It's being reflected in the environment, and by measuring the time of flight it takes for the laser to come back to the sensor, you can actually make a range estimate. As you do this and you scan the environment, there's multiple lasers here. They're colored differently. There's a blue one, a yellow one, a red and a green. They're all infrared, they're just colored differently for display purposes. As you do this and you integrate over your position, you can actually build up this 3D point cloud, very much like a video game. And this 3D point cloud allows you to make assessments as to what is drivable, what's not drivable. So if you look in this display alone, you can see on the left side of the vehicle, from your perspective, kind of a mountain, a hill. On the right side, you see a big negative obstacle, which is a cliff, essentially, in a big valley. Here's the same thing after data processing. This is a typical map that the vehicle would build. In fact, this is taken from the race itself. You can see the GPS breadcrumbs are these big X's in blue. And the red area are areas that the vehicle deems to be unsafe to drive. There might be negative obstacles like a cliff, or there might be berms or ruts or something similar. And in doing so, it's able to do microscopic navigation. That might look simple to you, but it turns out it took about 3 years of hard work to get to this point, as illustrated by the first sprint challenge. We also use vision a lot. Vision is the parallel of human eyesight and robotics. So we have a camera on there. The problem with the camera is it's really hard to write a piece of software that finds drivable surface. If you look at this image over here, what type of software would you write to discriminate, say, the road ahead from the vegetation left and right? The first thing that my students did is they wrote a color detector, so the road is typically gray. But it turns out some roads are overgrown with grass, others are paved, they're not gray. So it didn't work. And then they moved on and said maybe the road is the smoothest thing in the image. Yeah? So the smoother something is, then the closer to adjacent pixels are in color, no matter what the color is, the more likely it is to be drivable. But what you get with this is a perfect sky detection, because the sky is the smoothest thing in the road. So you always have to aim for the sky, which in general Stanford students should do, but not in these races. What we ended up doing is a very clever trick, which since started the entire DARPA program, called adaptive vision. We had these very, very short range sensors, lasers that wouldn't reach very far, but in their short reach could really perfectly find road and drivable surface based on a 3D point cloud. Then you could do machine learning to train a system to understand what the road looks right now in terms of color and texture, and then apply that machine learning estimate as the robot moved to the entire scene to find roads further ahead. And doing so, we would find similar colorations to what's just been found to be drivable right in front of you, further out, giving us a chance to react much earlier and thereby to drive much faster. So here's a typical situation. In the desert, where you can see a desert trail. It's the same mountain pass I kind of showed you before. The coloring means, red means likely drivable, green means likely undrivable. It's not perfect by any means, but it's good enough to spot big obstacles ahead of time and then slow down. And if you do this, the laser would eventually be good enough at its short range to avoid collisions. The race itself took place in 2005, so it's quite a few years back now, and I'll move on to more recent stuff in a second. But it was a fascinating race. We all met in the Mojave Desert. A couple of luminaries came, including various Google founders or Apple founders happened to hang out with us. The robot started at 6:30 in the morning, just at dawn, and they were all unmanned. There was no person inside. They were completely autonomous. They were being followed by a human-driven car, by the organizers, by DARPA. They had a kill switch in case something went wrong. But other than that, the car would drive by itself. So the feelings that we have are really bizarre, because normally when I'm in a race, I run marathons, I do bicycle racing, the moment the race takes place is the hardest moment, where I sweat the most. Whereas here, you just push this little button, right, and then the race begins, and you're just sitting there, right, eating breakfast, drinking champagne, and you wonder what happens to your car. The best comparison I have is, for our feeling, is if some of you have sent kids to college, right, so you worked on them for the last, 18 years, they're really perfect, okay, and then you send them out and go to college, away from home, and you wish they come back without any dents, like scratches, right, or not pregnant. Whatever you care about as a parent, the same you care about as a robotics engineer. So here you see our car driving by itself as videotape from a helicopter. This is our big, fierce competitor, Carnegie Mellon. The view that we actually saw in this race was just a web view. This is an accelerated view of the course. The course is very kind of internested, so it's hard to say how far these vehicles have progressed, but you could watch a little green dot moving along and turn red, like this car did, by Caltech, who had a little ambiguity in the interpretation of GPS waypoints. These guys, at some point, decided to ignore obstacles. So did these guys, actually. They actually lost the laptop. They had strapped on a laptop that went out of collision avoidance, and that strap came loose. Just kind of sad. Carnegie Mellon went into an impasse, our big competitor, and had a fuel supply problem, which made their lead vehicle, the two vehicles in the race, slow down, and that gave us a chance to reduce the distance. We had started about 5 minutes later. It's a time race, a staggered start, and now we were able to reduce the distance to about a minute, as shown in this nice helicopter shot that we got from Nova. About 103 or 4 miles into the race, we got this final moment where we were actually able to pass Carnegie Mellon's robot. So here's our only man-made obstacle we ever encountered in the race. It's a robot that's being paused. The pause time doesn't count against Carnegie Mellon. And our robot not autonomously decides not to hit it, but to swerve around it elegantly like the bush before to take the lead in the race. The race then progressed through a treacherous mountain pass where, by all means, our robot Stanley had to make life or death decisions. So you can see descent here, followed by its pursuit vehicle. This mountain pass is actually drivable. It's a drivable road. but it's confining and it's tricky. You wouldn't want to do this drunk. The car is completely covered in dust, so its sensors mostly don't work, which makes it go faster. But then it has a little logic that says whenever the ground is too bumpy, slow down. So it goes about 15 miles per hour right now, crawling through this mountain pass. And when it finally managed to descend through this area, which was by far the most difficult terrain, we all knew that there was a chance of actually finishing this historical race. So we all went outside. First we saw 2 helicopters in the air, then we saw a dust cloud. The dust cloud turned into a little blue dot. The blue dot grew. And about just below 7 hours into the race, 6 hours 53 minutes, Stanley, covered in dust, emerged completely autonomously at the tire finishing line. And we are in the back somewhere celebrating. On the right side, this is Stanford. On the left side is Carnegie Mellon, not celebrating. We were completely lucky, I should say. So in America, I've learned that the winner always matters the most, and the second one doesn't really matter. But we're completely lucky. It turns out that Carnegie Mellon having a food supply problem, they would have clearly won. So my quote at the end of the race, that was in Nova and in television, was that I think we believe everybody won in some sense. It was really a victory for the community. Well, Wired magazine liked us. They called us the best robot ever. And now if you go to Washington, D.C. and stop by at the National Museum of American History, there's a whole room dedicated to Stanley and a motorcycle with an entire exhibition around it, about 1,000 square feet. It's really fun watching and checking it out. So Stanley's finally at his graveyard. Then move on to a new challenge that DARPA designed called the Urban Challenge. The Urban Challenge accounted for the fact that the Grand Challenge had nothing to do with traffic. Whereas if you ever drive anywhere in Iraq, Afghanistan, or wherever you wish, you have to worry about other traffic. So DARPA came up with an idea to make a race where there would be many, many cars at the same time, robots and human drivers alike. And these cars basically had to do, think of it as like a FedEx delivery truck. Run errands, go to this point over here, go to this point over there, find your own route. If a street is blocked, turn around, go some other way, park somewhere along the way, merge, and so on. So it wasn't quite as dramatic visually, in some sense. You can see the cars are moving very slowly. But it was really fascinating to deal with the topic of how you then interact with other moving vehicles that are unpredictable rather than just bushes and berms and ruts and so on. We finished first but came in second in the final ranking. This is the moment where Junior, our robot, pulled up to the finishing line, like a second before Carnegie Mellon, who then won. We're using now about the same technologies, a little bit more advanced. We have a laser that basically scans the entire environment. You can look to all sides, kind of surround sensing. That allows us to understand traffic, not just in front of us, but on the side of us. And here's a typical view of the situation in the race. This is a Google area image superimposed with local sensing, as shown in red. There's a car in front of us, a robot that basically cuts us off. I think that was Virginia Tech, took our right away. And behind it is chase vehicle that we cut off now. So the chase vehicle couldn't follow, a little chaotic in the race. But it gives you kind of the feel of the complexity. You can see the car moving along, a car in front of it crawling along, and us making decisions where to move best. Like in this case, we want to turn right into the side street. Part of this exercise involved being able to really understand other vehicles, something that hasn't been done in the field much before. Here's a camera image of a situation where there's oncoming traffic. These are actually brave stunt drivers who DARPA hired and for a premium salary. To put themselves into the cage with the lion. And you can see our vehicle being able to use this laser data on the left and being able to identify these moving vehicles and track them. Here's one of the videos that I'm very proud of that really showcases state-of-the-art in robotics today. This car now, completely autonomous, has to turn left through moving traffic. Around it are these stunt drivers about 10 miles per hour, very slow. And at some point there'll be a gap just barely big enough for Junior to fit. It's coming up in a second right now. It has then to turn left confidently, stay in a very narrow lane. It's way too narrow for GPS to give you good enough localization, so we do some other stuff. And then face this oncoming traffic and without a shiver, be able to drive along through this ring over here. And then go further. You can see all these cars crawling along. And then do the same thing again. Turn to this little small stub road, and wait and so on, and yield, and then turn left again. This is about the state of the art in ability to interact with other traffic in urban situations. And we do this about 30 miles per hour max right now on campus. So if you see a blue car coming towards you, okay, my number one recommendation is turn the other way, of course, right? Stay away, stay safe. But if you have no choice, it might actually face you at 30 miles per hour, which is differential speed of 60 miles per hour, which is pretty frightening from a software perspective. So you can see that the left turning in. Now there's lots of that we can't do. This is a traffic scene we can't negotiate yet. It's actually daily, and I was actually amazed. There's clear rules in India for driving, and they have to do with your physical size. Like the bus just goes. Other things you can do. Oh, we used not to be able to do this one. I really like this one, which is a way to park a car. You might have seen those all over YouTube, of course, and there's competitions for these. Now, actually, recently we are able to do this. So this works better backwards than forwards, but this is in Shoreline parking lot right next to Google. Completely autonomous. One of our students here at Stanford. And this is one which I want to get to because I'm German, as you probably all figured out. And as a German, I'm into precision. So you have to look on the right side. This is an actual traffic camera, an actual recording. And you have to look here when I tell you, okay? Not yet? Yeah. Wow. You see it? Anyone not see it? Okay, good. Everyone saw it. It's one person you can see it over here. Okay, so that's kind of the goal, to get to be able to drive a very close distance. Let me just play this again. Let's see me play it again. Right? Technically, it's completely feasible, right? If 92% of your road is empty, you can do this kind of stuff. You can go on a highway in opposite direction, it's feasible, right? It's just the guts, right? So that's something we should work towards. So just to finish my presentation, because I know I'm the guy between you and lunch, let me talk a little bit about the next steps ahead. And now I'm becoming serious again. This is a slide I showed in the beginning. I'm not going to go through it again, but I hope I convinced you there is ample opportunity in the field of transportation to really innovate. I'm thinking, for example, about mass transit. Obama is just investing a lot of money into high-speed trains right now. I think 86% of Americans use only cars for transportation to work, and 99% use cars and something else for transportation to work. So trains is not a successful proposition in this country, and will probably never be. Unlike in Europe, where I think it's fairly successful. But the downside of trains are great. So you can get inside the train, you can do work and so on. The problem with trains is that it's hard to get to the train and hard to get to work from the train. So you have to have some way of transportation. That's certainly the problem if you don't use trains. Now, what if your train of the future was your car, right? So you go on the highway, okay, and then you push a button, and your car links up with some other cars by itself at very close distance, saving you something like 10% of your gas expenses, okay, driving at high speed, completely autonomously for the next 30 minutes until you reach your exit. And then eventually the train opens up again, and you can drive out of your car and drive to work. Wouldn't that be amazing? Mm-hmm. Wouldn't it be amazing if you didn't have to park anymore, right? So you go to work, and you drop yourself off at your doorstep, and you tell your car, find somebody else to drive. Like, go home, pick up my spouse, right? Or find somebody else to drive around, right? So at some point, I think there's a vision here. You might be able to enable entire different models of car sharing that don't exist today. They were significantly reducing the burden we put in the environment, and on energy and other things. But it's being more rational about the resources we use in transportation as we are today. There's so many opportunities. If you take one thing from this talk, then the technology is basically there. There's bits and pieces missing. It's not as reliable as we wish it to be. There's situations where we can't drive good enough. But we've invested, how much money have we invested? We've invested maybe in the last couple of years, $10 million, right? So if you invest as much as has been invested in the iPhone, right, we can probably solve this thing in 2 or 3 years and really make significant progress. There's no technological reason not to engage in this kind of innovation. In fact, there's also no market reason. There's a number of products I think could be sold and for which I believe there's a market, like, for example, tandem driving for trucks, so that the trained truck driver can save gas and rest at the same time by an invisible axle, or the rental car that pulls up at your gate, right? So you go to your phone, you hit a button, and you check out your luggage and say, I need a car now, and the car just pulls up to you, so you save yourself the 20 minutes in the rental car counter. There's actually many different things we can build. Driving for elderly people, independence and quality of life at higher age really depends on mobility. We can build cars that make elderly driving safe. But I really believe there's a product path and a monetization path of this kind of technology. I really believe it's forthcoming. So what we really need, I think, is sustained openness towards the new technologies, as we've done in the digital information space, and start investing into new driving technologies. With that, I'd like to close and open the forum for questions. Thank you.
For more, please visit us at stanford.edu.